In this work, we present audiovisual SlowFast networks for video recognition. Before we start, let's first look at an example to see how audio can be useful for video recognition. As you can see, it's not easy to recognize the action class just by looking at the RGB pixels in this case. Whereas if we get to listen to the soundtrack of this video, the task becomes trivial. Another important reason why we want to use audio is because audio processing is much cheaper compared to its 2D visual counterparts. Before we get into how we do audio-visual modeling in this work, let's first look at how we humans do it. For this, I'm going to play a video here. Please pay attention to the lip motion.
Ba, 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 ba.
Okay, now let's play another video. Please compare this one to the previous video.
Ba, 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 ba.
Alright, as some of you might have already noticed, these two videos are with exactly the same audio clip, but with different visual frames. This fascinating phenomenon is called McGurk effect, and it demonstrates that when we humans fuse audio and visual signals in our brain, we fuse them at a fairly early stage, so that what we see will affect what we hear and vice versa. However, unlike how we humans do it, modern machine learning approaches take this very different late fusion paradigm, which means that they have different towers to process different modalities and only fuse their results at the very end. In contrast to these methods, in this work, we propose to go with this more theoretically appealing route to perform hierarchical audiovisual modeling. In terms of approach, we based our method upon this previous work called SlowFast networks, which has a slow pathway that's responsible to extract out semantics and a fast pathway that's responsible to extract out motion information. Based on that, we propose audio-visual SlowFast networks, which added this third pathway that's dedicated for audio processing. In a sense, this third pathway can be thought of as an even faster pathway, as the sampling rate of audio signals can easily go to the order of tens of kilohertz. Moreover, since it's 1D signal, it's also cheaper to process. The first problem we encountered when we train our audio-visual model is this issue of training dynamics mismatch. Here, I'm showing the plot of the train and validation error of both the audio-only model and the visual-only model. As you can see, these two models differ drastically in terms of their learning speed. Specifically, it takes something around a third number of iterations before the audio model starts to overfit. And this is a big problem because it means that when we train our joint model, it will easily overfit onto the audio input and thus not being able to generalize. In order to address this issue, we propose a simple but surprisingly effective technique called drop pathway. Essentially, during each training iteration, we randomly drop off the entire audio pathway with certain probabilities. This way, we slow down the training of the audio pathway and thus make these two modalities more compatible with each other. In terms of the effectiveness of our approach, the short story is that our AV SlowFast model achieves state-of-the-art performances across all different datasets and tasks, with very modest computation increase, sometimes as low as only 2% increase, which shows that audio can be a very economical add-on to the state-of-the-art video recognition pipeline. We also analyzed the per-class results on kinetics. As can be seen, classes that benefit the most from audio include dancing, whistling, and beatboxing, which all have very distinct sound signatures. Whereas for classes that bear the largest performance loss, you can see that they either do not have a strong sound signature, like in the case of massaging legs, or it is one of those classes with strong background noise, like in the case of skiing. Finally, we further extend our AV SlowFast into the domain of self-supervised video representation learning and demonstrate state-of-the-art results using the existing audio-visual synchronization pretext tasks. Okay, that's all, and please check our paper for more details. Thank you.